Hi everyone. I'm passionate about getting undergraduate and high school students into the research environment, doing authentic research as early as possible, but I know that doing this is completely non-trivial. So I'm going to tell you about how I did it in New South Wales context, supported by the high school syllabus that we've got in New South Wales. And hopefully this will give you some inspiration in your particular context about how you might like to achieve similar goals. So why do I want to do this? Because as an undergraduate student, I benefited so much from having experiences in a very diverse range of fields, from astronomy, synthetic chemistry, laser spectroscopy. I looked at quantum consciousness, all sorts of different projects. It enabled me as a PhD student to know exactly what I wanted to do and why I wanted to do it. And I think really defined my career. And I got involved in this way back as a high school student. This is a project I did in year 10, where I'm a theoretical chemist. My dad created this windmill and I used a normal fan, and we had 6 spindles and 4 spindles, and I was trying to figure out which one would be the most effective. And this little high school project actually got me all the way to the US from Australia. We went and visited the Grand Canyon, and I took place in the International Science and Engineering Fair, which really was a pivotal experience in my life and scientific journey. And my goal is to give this to as many people as I can. And within the Australian government context, we've actually got this new government push for work integrated learning, which is really about getting our students experience within the workforce so that they're more career ready. Experience within the science and chemistry research laboratories, what we in Australia call research integrated learning, has many of the same outcomes, but it's, in my view, a lot more scalable within Australia, within science, because the people that deliver research integrated learning are academics within the university system. And hopefully the lessons that I'll tell you today about implementing SciX will apply to work integrated learning, research integrated learning in a variety of different experiences, where instead of giving students a course-based curriculum, we give students a project-based experience where they can learn authentic workplace skills. So this is a science extension course in New South Wales.
The Year 12 Science Extension syllabus is an exciting new step in creating tomorrow's scientists. The course focuses on students using authentic scientific research skills to produce a research report, just like real scientists do. Students will apply these scientific research skills to find solutions to today's problems. This is a practical, forward-looking syllabus.
This is supported by external academic business partners like us.
So that is the goal. What is the issue? The problem is that there we heard about 2 top achieving students, but we want to scale this to 800 students in New South Wales. Where's the money? Where's the time for developing the resources, supporting the students? So I actually started on this journey in the UK with the Orbits program, original research by young Twinkle students. So when I moved to Australia, one of my goals, and I was supported by lots of other people here, was to develop scalable, sustainable research experience for, in this case, 65 students. Now we're up to about 175 a year. How can we do this year on year on year?
I'm here at UNSW in Sydney doing a SciX summer school program. The project we're doing at the moment is exploring human genome to understand brain disease.
So the benefits that I found joining SciX at UNSW, I really enjoyed how well organised everything was, and I really felt that I worked well with everyone here, including my mentor and my lead academic.
It was really cool. Spent the whole week here, used telescopes during the day, didn't know you could do that.
Hands-on to make it like the best possible experience for the student.
And it's really cool how we've got a PhD student and a professor here helping us work on it, and really nice people from what I've heard from other groups who are doing other things. It's really cool. They're really excited about what they can do with the science extension.
And I'm here at UNSW doing the SciX summer school program.
So with SciX, we've got a 1-week program within our summer holidays where they come in on campus, hopefully, and learn research and explore their own hypothesis in a supportive environment. And that might be a laboratory project, computer program, or instrument work, depending on what project they're doing. We do take them to the research labs, engage them with researchers that are going on. They get to experience life as a university student in lecture theatres if they'll continue. and definitely our active learning classrooms, which are a pivotal part of our experience. Now, one of the things I'm most proud of with SciX is that this experience isn't limited to the high achieving students at well-resourced schools. Instead, we actually get 40% of students that are fee waiver students, which means regional, rural, low socioeconomic or similar. And we actually got 68% female enrolment in 2022 without any targeted recruitment. That was just our raw numbers. So that's pretty exciting opportunity and demonstrates the power of this sort of scalable approach. We've had very high student satisfaction. So for on campus in 2020, we got 4.9 out of 5, which was amazingly rewarding. So the thing that they loved the most was interacting with the PhD students, with their mentors. They developed all sorts of skills, especially when you're dealing with computational skills. The other statistic I wanted to highlight here was their self-identity as a scientist. In just 1 week, they're increased on this scale of 1 to 7 from about 3.8 to 4.7 on average. And this increased sense of belonging and sense of community, I think, was really the powerful point of getting everyone in one group doing research for a week supported by mentors. In my view, to make a program like SciX work long-term, it needs to benefit not just the students, but the people delivering the projects. And these are our mentors from SciX 2020. And they're PhD students, and they're learning project management, people management. They're supervising for the first time. They're teaching independently, developing resources. And I know that this is an incredibly valuable experience because when I did it in the UK, I actually learned how to supervise students. And so when I had my own PhD student, I wasn't petrified because in my case, I knew that I could publish papers with these high school students. I knew how to deal with a student that really wasn't participating a lot in the research. And eventually I learned how to take my hand off the mouse, but we learn. So in my view, to have a sustainable and scalable high school research program or undergraduate research program, you need 4 things. The first is you need to design your projects properly so that they don't take too many resources but are fun and exciting for students. The second is you want to tailor your program for the local context. So can they get course credit? Can they get university admission credit? Where are they going to have time to do this project? First, have exams and other competing interests. The third one is, where is the funding coming from? Is there philanthropic? Is there government funding? Is there university funding? And we also need a scalable team structure so that you can go from 65 to maybe 250 students and keep making it work. So from my experience designing high school and undergraduate research projects at a whole variety of levels, I've come up with the acronym PROBA, which means one who inquires. And in particular, I think whenever you're designing a project, different contexts will have different priorities in this space. First of all, how important is it for you that the research is publishable? Second of all, what resources do you have for your project? So is the software free? Do you need lab resources? Do you need money? And also, do you have the expertise in your local environment to support that project? The third one is ownership of project by individual students, and this tends to compete with the publishability. In the SciX context, because of the science extension syllabus, we needed very high ownership of the project, but that meant that it wasn't publishable. Whereas in Orbits, it was the reverse. We didn't need ownership of the project, and therefore it is publishable research, and in fact, we've had multiple publications from it. The background required means what scientific knowledge do students need to know. The less, the better, and the more in line with what they might learn in first year uni, for example. That's appropriate background. Specialised knowledge that is only relevant if you're going to become a spectroscopist, probably not the best. The excitement factor or interest is basically how you attract the students. So are they going to be more excited about a computational chemistry project or an astrochemistry project? The repeatability, I think, is really important for many cases. The repeatability is important because designing projects and developing all the resources is extremely time consuming to do it properly. And therefore, you need to be able to repeat a project in many programs year on year with adaptations, but not a full project redesign. As we go from high school research projects through undergraduate projects all the way up to a PhD, things change. These priorities shift. Background obviously can increase in complexity as you go towards a PhD. The ownership generally increases, but SciX, it's quite high, and that actually creates problems with this publishability aspect. The resources, generally the higher, the more advanced you are, the more resources you can devote to a particular project. The repeatability goes down, and the excitement generally has to remain high. Though once you get to a PhD, it can be a little bit more esoteric. You don't need to be able to explain it to your grandparents exactly what you're doing in a project. So to make that discussion concrete, I want to consider the projects that I've done in my research field, which is computational molecular spectroscopy, mostly for astrochemistry. So MARVEL is a process by which we get all the experimental data that's known on a particular molecule, digitize it, put it into a computer, and then we get the empirical energy levels, which are really, really important for spectroscopy and analysing stars. And in this project, I've supervised 2 projects in this area for orbit students, both of which have been published. The publishability of this is obviously very high. The resources were quite easy because it was a browser program, Excel. The digitizer wasn't trivial, but we only had to buy that once for me, and that was fine. The ownership was very low. The background, astronomy is of general interest to most people. The spectroscopy was mostly second-year physical chemistry content of general usefulness, even for high school students. The details of quantum numbers, not so much general usefulness, that was more for this specific program. But because we were talking about aliens, stars, space, the excitement was high, and the repeatability is very high because you've got molecules for days. Now, the second time I did this, I went, okay, I want to increase the individual ownership, so I'll give everyone a molecule. And I'm in this field, I love diatomic molecules, and I thought, well, let's update a data set. And I created all these nice lessons. I learned, we did some online databases, which was a beautiful online database. And then I gave it to students. Never seen something fail so miserably. These are prober priorities. And the important bit here is that diatomic molecules were not exciting to students. And therefore, the whole project honestly just failed. The third project I did in this space was the SciX project, the approximate spectroscopy of biosignatures. So we're trying to find aliens. And we do this by putting a molecule into a computer program and calculating its infrared spectra. Pretty easy to show them how to do that. Each student designs their own set of molecules, determines their own research question. For example, can you detect CFCs in the atmosphere of water and carbon dioxide? So can we find alien pollutants? The publishability is reasonably low, but honestly, I used it to test ideas and prepare for PhD projects, which are now going exceptionally well. And so within the SciX context, I've come up with the following steps. One is that you need an academic lead to provide oversight and mentorship, but the mentors, which are normally PhD students, are the ones that definitely run most of the project, especially after the first year. And for one mentor, you've got about 6 high school students. That ratio seems to work brilliantly. The exciting context is number one. You have to recruit the students. It needs to be interesting and exciting. The research or data collection or analysis technique, you find one tool that you can teach to lots of students and apply it to individual multiple hypotheses. And that last bit is where you get the opportunity for student expression and creativity. And so if we put our astronomy project in there, we've got a team, and as one PhD student graduates, my next PhD student, I recruit students that tend to be interested in outreach. So I've normally got someone who's interested in delivering the project. It's relevant for exoplanets, but also for climate change. They have a tool and they figure out a research question. In general, in the SciX context, the common types of projects are computer programs, where they basically run a simulation, a large online database, which tends to work really, really effectively. So astronomy archival data, a large online database, which tends to work very effectively, though not so much in the chemistry context. Chemistry-wise, everyone loves an experimental procedure. It's not trivial to make it happen. One, because the resources are very high. And two, in the SciX context, we need them each to have a different hypothesis, which means you need 6 different functional groups, materials, etc. So here's some chemistry SciX projects. So the first 2 are computational. Batteries is a more database project. MedChem, NanoMed, protocells, and cells are programs where they're doing synthesis, some instrumentation, and then some hypotheses that are going on there. And I think the really important thing is here we're talking about medicine, we're talking about aliens, batteries. It's all very applied and useful, and therefore it's pretty good at recruiting students to the project. So in terms of the timeline that you need to go through, in terms of the timeline here, I wanted to highlight that It's actually a 6-month process between. So we've got our timeline pretty sorted at the moment with SciX, and I want to point out it's a 6-month window between when we start the project recruitment, we go through very scaffolded project design, we promote to high school students, then they enroll, and then we develop the project, and that takes about 10 and 20 hours respectively, and then we develop and deliver the program and have some post-summer school opportunities. This project design and project development do not skim on these, because this is what dictates how well the project goes in practice. I'm more than happy to talk to you about details. So here's some examples of the projects I've talked about before. One thing I will point out is Python works extremely effectively. Just ask them, just do everything via Jupyter notebooks. Do not touch the terminal. Just get them to download Anaconda. It's worked brilliantly. I give them a bit of Python pre-work before, works well. The other essential component of SciX, and an appropriate concluding slide here, is that this takes an army to make it happen. So this is a SciX delivery team for just 65 students in 2020. And that doesn't even include all the academic leads and the admin support that was behind the scenes. And for 2022, with 175 students, we have a delivery team of more than 50 people. Huge thank you to absolutely everyone who I couldn't list on this slide because it would have been too many people, but this whole team is really needed to make SciX work effectively. Thank you very much.